Yes, children. So let us proceed with more details about electromagnetic spectrum, right? Okay. Now, first of all, we have to understand what is a spectrum. Spectrum is nothing but a set of different colors which are formed when a source of light is passed through a narrow slit. Slit is nothing but a narrow opening, a small hole on to a prism, and the different colors present in the white light, they deviate. So this is what you call it as VIBGR. V for violet, indigo, blue, green, yellow, orange and red. So this you know it. Now here what you see, violet is deviated the most and red is deviated the least. And the one which is deviated the least has longer wavelength, and the one which is deviated the most, this will have shorter wavelength. And this is the reason why red color is used as signal. You can see red color from a very long distance, is it not? Because it's having a longer wavelength, it is visible to your naked eye even from a very far off distance. So this is the basic concept. So when white light is passed through a prism, the wave with shorter wavelength bends more than the one with longer wavelength. So red has the longest wavelength and violet has the shortest wavelength. So violet is deviated the most and red is deviated the least. That is why it is seen from a long distance. So this is about the basic idea about what a spectrum is. That is, white color is splitting into different colors. Now the same kind of concept we are going to apply in terms of the electrons present in an atom, how they are getting excited, and when they come back to their normal level, how they are emitting energy. That is what we are going to see in terms of spectrum. So you know very well, you have studied Bohr's concept in 9th class. You know that the electron, they jump from one level to another level and they will come back to their normal level, to their original level. All these things you have studied. So let us go into details about all these things. So the different levels where the electrons are jumping, let's say from K shell to L shell or K shell to M shell, these levels, K shell, L shell, M shell, what are they called? They are all called as quantized energy levels. Now what is meant by quantized? Restriction of any property to a discrete value is called quantization. Each and every level is associated with a definite energy. That is what you call it as discrete values, definite value. Their energies are constant. Every energy level has a constant energy associated with it. Okay, now let's go into details of what an emission spectrum and an absorption spectrum means. So spectrum is of two types, emission spectrum and absorption spectrum. Let us see what they are. Now what you see here, you see here a glass tube which is filled with hydrogen gas and it is connected to a battery. Now when energy is supplied from the battery, what will happen? This hydrogen will first split into two individual hydrogen atoms. Now once they split into hydrogen atoms, you know very well that hydrogen has an atomic number 1. So it has only one electron. Because of the energy that is supplied, these electrons, they will absorb the energy and they will jump to a higher level. Whenever energy is supplied, some work has to be done. So what it does, it jumps to a higher level. but it knows very well that it cannot remain there forever. It has to come back to its original level. So when it is going up from its K shell to either L shell or M shell or N shell, it will absorb energy, and from those higher levels, when it is coming back to its own K shell, then it will release all that energy what it had absorbed. Now that released energy is our source of light. Got clearly? Whenever energy is supplied to a gas tube containing hydrogen gas, first it will break into individual hydrogen atoms, and the electrons of the hydrogen atoms are excited, and these excited electrons will go to higher level and they will come back to their normal level. When they go to higher level, they absorb energy. When they come to their original level, that is lower level, it will release that energy. So that released energy is, that energy is our source of light. Now that released energy in the form of light is passed through a narrow slit onto a prism, and it splits into different colors or different wavelengths. So this is what you call it as emission spectrum. It is directly from the source. Why it is emission spectrum? Because the spectrum of colors that you are getting here, it is directly emitted from the source. This is called emission spectrum. Now what is absorption spectrum? In the case of absorption spectrum, what happens? There is a source of light, and this source of light is passed through a particular substance. It may be any substance. Say it is placed inside a beaker. Now when the light is passed into this substance, some wavelengths of the light the substance may absorb, and some of the wavelengths it will release. The wavelengths of the light source will be absorbed by the substance. Some of them will be absorbed, some of them will be released. So some wavelengths have been absorbed by the substance. Now whatever is not absorbed will come out, will get transmitted, and that is passed through a narrow slit onto a prism, and you get a spectrum of colors. Now here what you find, and here what you find. Here you find a dark base on which bright lines are seen. Now the background is dark, and these are colored lines in the case of emission spectrum. Whereas in the case of absorption spectrum, what you have the set of colors. This is one color, this is one color. One color is merging into the other, and you find dark lines on a shade of colors. So the dark lines represent the absorbed wavelengths, whereas here the colored lines represent the wavelengths which are released. So what they say, this emission and absorption spectrum. Absorption spectrum is a photographic negative of emission spectrum. So this is about spectrum, which is called as emission spectrum and absorption spectrum. Now we are going to see about this hydrogen spectrum, which is emission spectrum here. Now in this case what happens? We saw that the hydrogen atom is having one electron. Each and every hydrogen atom having that one electron. See, certain hydrogen atoms will absorb lesser energy. A few more hydrogen atoms may absorb more energy. So depending upon the energy that they have absorbed, the electrons, some of them will go from K shell to L shell only, and some of them can go from K shell to M shell also, or to N shell also. Okay, so these L, M, N, what are they? They are all imaginary space around the K shell of the hydrogen atom. They are all imaginary spaces around the K shell of the hydrogen atom. So whichever electron has absorbed more energy will rise to a higher level. Whichever has absorbed to a lesser energy will rise to a lower level. So now here, depending upon the energy absorbed, you will get the emitted energy. Emitted one will also fall in the form of a spectrum, because each and every electron is releasing different amounts of energy. One set of electrons may have jumped from K level to L level. So these electrons will give out a certain amount of energy. Some of them might have jumped from K to M shell, so that will release a particular amount of energy. And those which have gone to N shell, they will release another amount of energy. Right? Okay. Now what happened? This line spectrum of hydrogen. What they did was experimental observations, which Bohr, a scientist, he showed in the year 1885 on the basis of experimental observations. If the spectral lines, see each and every, on the spectrum you have lines, is it not? Spectral lines. They are expressed in terms of wave number. Wave number is what? Nu bar. This is called as wave number. They are expressed in terms of wave number. Now this is in accordance with a particular formula, that is nu bar is equal to 109677 into 1 upon 2 square minus 1 upon n square centimeter inverse, where n is an integer which is equal to or greater than 3. That is, your n will be equal to 3, or it may be 4, 5, 6, etc. It may be either equal to 3 or greater than 3. Now, the series of lines described by this formula is called as Balmer series. Why we are very particular about Balmer? Because the Balmer series of lines are the only lines in the hydrogen spectrum which appear in the visible region of the electromagnetic spectrum. The set of lines or the series of lines fall in the visible region of electromagnetic spectrum. Since it was visible to naked eye, this was found first. So according to Balmer, you know very well that nu bar is equal to 109677 into 1 upon n1 square minus 1 upon n2 square, where n1 carries a value of say 1, 2, etc. and n2 will carry a value of n1 plus 1, N1 plus 2, like that. That is 2, 3, 4, etc. Now this value 109677 centimeter inverse, this is called as Rydberg constant for hydrogen. Now like this, various other scientists by the name Lyman, Balmer we have already seen, Paschen, Brackett and Fund, P is silent. These people also, they have given their own concept about this line spectrum of hydrogen. Now how they studied? Balmer, what did he study? He studied when the electron has been shot up to the second level, and when it comes back to its normal level, that is 1, what is the amount of energy released? So what he studied that when from the second level. So the assumption here in the case of Balmer is the electron is there in the second shell, that is L shell, and from the L shell it is now going to the third shell or the fourth shell or the fifth shell, like that. So Balmer, what did he study? He studied the electron moving from third, fourth, fifth level to n is equal to 2. When the electrons are present at the third shell or the fourth shell or the fifth shell, when it is coming back to second shell, what is the energy released? What is the wavelength of the light that is released? That was studied by Balmer. Now what did Lyman, what did he study? He studied the electron when it is jumping down from second, third, fourth, etc. level, that is higher level, to n is equal to 1. Balmer, the set of lines observed, they were falling in the visible region of spectrum. That is why this was first of all known. What Lyman studied, this was falling in the UV region of the spectrum. Then you have Paschen, when the electron moves from 4, 5, 6th level to n is equal to 3. What is the energy release when an electron jumps from 4th level to 3rd level? When an electron jumps from 5th level to 3rd level, from 6th level to 3rd level, what is the energy release? That was what was studied by Paschen, and the corresponding spectral lines were found in the infrared region. In the case of Brackett, the electron is moving from 5, 6, 7, etc. to n is equal to 4, and this is also falling in the IR region only. And Fund, the study that he conducted, he studied the energy of the electron when it is moving from 6, 7, etc. to n is equal to 5. And this also fell in the infrared region. So Lyman spectral lines, he got it in the ultraviolet region. Balmer got it in the visible region. Paschen (Fund), they all got it in the infrared region. Right? So this is what you call it as line spectrum of hydrogen. This was the basis for understanding the electronic structure of atoms. So this is what is given in your textbook also. You can see the diagram. See, this is n is equal to infinity, n is equal to 6, 5, 4, like that he has given. Now look at the Lyman series. When the electron is falling from 6th level to 1st level, 5th level to 1st level, 4th level to 1st level, 3rd level to 1st level, this is what is called as Lyman series. Then what did Balmer study? When the electron is jumping down from higher level to 2nd level, that is n is equal to 2. What is n? N is nothing but the shell number, samajh lo. And what did Paschen study? Paschen study when the electron moves from higher level to n is equal to 3. Bracket, what he studied? When the electron falling from higher level to n is equal to 4. So like that, different spectral lines were observed when they studied the line spectrum of hydrogen by supplying different energy. Each one is supplying different amount of energy. Is it not? You are having a gas tube filled with hydrogen and energy from a battery is given. So depending upon the amount of energy supplied, the electrons are also absorbing different amount of energy. So that is why they are going to from higher level to lower level when they are falling. What is the wavelength of the energy release? That was studied. So this is the diagram showing the transition of electron in the hydrogen atom. Because it was basically hydrogen is the simplest atom because it is containing only one electron. So the study was much simpler. They were able to understand the concept much more clearly. Now comes Bohr's model. How an atom, what is the structure of an atom? That is clearly understood by means of Bohr's model. Right? Okay. So I just wanted to show you, like you see here. In the case of Lyman, I told you from higher levels to n is equal to 1. Supposing let us take a standard of 6 is the highest level. 6 to 1, 5 to 1, 4 to 1, 3 to 1, 2 to 1. So how many spectral lines you are getting? You are getting 5 spectral lines. Now in the case of Balmer, from higher levels to 2nd level, when the electron is falling, what is the amount of energy released? That is what he studied. So how many spectral lines he got? 6 to 2, 5 to 2, 4 to 2, 3 to 2. So 4 spectral lines he got. Then Paschen, how many he got? He got 3 spectral lines. From 6 to 3, 5 to 3, 4 to 3. Then what about Bracket? He got 2 spectral lines, 6 to 4, 5 to 4. How many Fund got? He got 6 to 5, that is only 1 spectral line. So in totality, if you see how many spectral lines are possible, it is 5 plus 4 plus 3 plus 2 plus 1, which counts up to 15. So how many spectral lines are there? 15 spectral lines are there. So if you know what is the nth level, that is the highest level, then you can easily find out how many spectral lines are possible for a particular atom undergoing, for an electron which is undergoing this kind of transition. That is given by the formula n into n minus 1 upon 2. Now here n is considered 6 because we are taking the highest level to be 6. So what is n minus 1? That is 5. So 6 into 5 upon 2, that will give you the number of spectral lines, that is 15. supposing if the highest level was say 5, then 5 into 4 upon 2, so 10 spectral lines are possible. So like this you can calculate how many spectral lines are possible. Now let us go to Bohr's postulates. What is the study conducted by Bohr? What did he say? What are the points that he put forward? They are called as Bohr's postulates. An electron present around the nucleus moves in circular orbit associated with fixed energy, quantized energy. These orbits are called stationary states. What are they? They are K, L, M, N, etc. So an electron present around the nucleus moves in circular orbit associated with fixed energy. This you have to remember, and they are stationary states. Why do you call them stationary states? Because these orbits, they don't move, only the electron is moving. Since the orbits are stationary, they are called as stationary states. Then the second postulate is the energy of an electron does not change with time so long as it is in the same orbit. If the electron is belonging to say second orbit, its energy will also be fixed. If it belongs to third orbit, then its energy will also be fixed. So the energy of an electron does not change with time so long as it is in the same orbit. Now when the electron is supplied with some energy, then the electron absorbs energy, it moves from a lower level to a higher level, or whenever the electron has to come back to a lower level, energy is released when it is coming from higher level to a lower level. So this difference in energy is given by the formula delta E is equal to E2 minus E1, that is final level, energy associated with final level minus energy associated with lower level. And I told you in the previous lecture already that E is proportional to nu, or E is equal to h nu, and nu is equal to C upon lambda. So you get delta E, that is the change in energy associated with any electron transition, is equal to h nu, or it is equal to hc by lambda. Now what is the energy associated with an electron belonging to a particular energy level? That is given by the formula En, where n is the orbit to which the electron belongs. That is equal to minus 2 pi square m z square e power 4 upon n square h square. Now here, whatever I have shown in this bright green, they are all constants. 2 is a constant, pi is a constant, this m is nothing but mass of electron, that is a constant, z is nothing but atomic number for hydrogen is 1, E is nothing but the charge of an electron, n is nothing but the orbit to which the electron belongs, and h is nothing but Planck's constant. This relation is called as Planck's relation. E is proportional to nu, so h is nothing but Planck's constant. So all these things are constant values. So if you put all the constant values, you get to the formula, that is minus 1312 upon n square kilojoule per mole. Now this can also be written as minus 2.18 into 10 power minus 18 upon n square joules per atom. This per mole has been converted to per atom. So here, whenever an electron is falling from say E2 to E1, there is release of energy. So when an electron undergoes transition from one level to another, the change in energy associated is what is shown as E2 minus E1. Okay, so this is what is called as Bohr's frequency rule. So when it is equated to h nu, what is nu? That is frequency of this electron transition. That is delta E, change in energy upon Planck's constant. E1 and E2, they are energy of lower and higher level respectively. So this is one postulate. Then the next one is, an electron can move only in those orbits for which its angular momentum is an integral multiple of h upon 2 pi. What he says, the electron can move, say from first shell to second shell it is moving. Now that second shell corresponds to an angular momentum which is an integral multiple of h upon 2 pi. Angular momentum. Momentum is nothing but product of mass and velocity. Angular momentum is product of mass, velocity and radius of the orbit. So this r. So whenever you draw radius, then you find an angle subtending at the center. So MVR is equal to NH upon 2 pi. So corresponding to the distance, that is r, you will get a fixed value for n. See, m is a constant, v is a constant, h is a constant, 2 pi is a constant. So the value of n, which has to be in the form of integers, say 1, 2, 3, etc., will decide what is the radius of the orbit. If this n has to be either 1 or 2 or 3, correspondingly this radius of the orbit will be decided. So that is what is the postulate. Electron can move only in those orbits such that n should remain as either 1 or 2 or 3. Corresponding to these values of n, the angular momentum is an integral multiple of h upon 2 pi. The radius will depend upon that. So that is another postulate. Now let us see what is radius of the stationary state. Radius of an orbit, say nth orbit. This is equal to n square into a naught. The value of a naught has been found to be 52.9 picometer. So radius of the first stationary state is found to be 52.9. That is, n is equal to 1. So 1 square is also 1. So 1 into 52.9 is 52.9. So radius of the first orbit is 52.9 picometer. So if you want to find out the radius of the second orbit, then this should be 2 square into a naught. So this is one concept. Then what is the energy of a stationary state? Energy of a stationary state, energy of an electron belonging to a particular orbit, it is given by the relation En. Say energy of an electron belonging to nth orbit is equal to minus RH. This H represents hydrogen atom, Rydberg's constant for hydrogen atom, into 1 upon n square. Now what is the value of this Rydberg constant? It is 2.18 into 10 power minus 18 joules. This is the value of Rydberg constant. So energy of the ground state. What is meant by ground state? The electron of hydrogen belongs to which orbit? K shell. What is that K shell? It is the first orbit. So n is equal to 1. So energy of the ground state of electron for hydrogen is minus 2.18 into 10 power minus 18 into 1 upon 1 square. So it is the same. Supposing if you want to find out or calculate the energy of an electron belonging to second orbit, then it is E2. So here n is equal to 2 you have to put. So that will be minus 2.18 into 10 power minus 18 into 1 upon 2 square. So correspondingly you will get the value in joules. Now you can also find out the energy for hydrogen-like species. Hydrogen-like species means what? He, it's having 2 electrons, but He plus has 1 electron like that of hydrogen. Li has 3 electrons, but Li2 plus has again 1 electron like that of hydrogen. Same way Be has 4 electrons, but Be3 plus has 1 electron as that of hydrogen. So they are called hydrogen-like species. In such a case, how will you calculate the energy? Energy of an electron belonging to nth orbit is equal to minus 2.18 into 10 power minus 18 into z square upon n square. So if you're talking about an electron of any other atom other than hydrogen, this z has to be used. It's very, very important. Same way, if you want to find out the radius, it is 52.9 into n square upon z if it is for any other atom other than hydrogen. Now the most important question here is, why is it that the energy of an electron belonging to any orbit, why it is shown as a negative quantity? Why it is a negative? Because you consider energy of an electron which is placed at an infinite distance from the nucleus to be equal to 0. You assume that the energy of an electron placed at an infinite distance from its nucleus is said to be having 0 energy. So E infinity is 0. Now, what happens when it is at a very far distance? It is coming towards the nucleus. When it is coming towards the nucleus, what you have studied, when it is falling from a higher level to a lower level, energy is released. Energy at infinite distance is 0. Now, when it is coming towards the nucleus, it will release energy. So, from 0, if energy is taken out, then obviously it will become negative. Is it not? Less than 0 is what? Negative. So that is what I have written. Energy of an electron in an atom is lower than the energy of a free electron at rest. Free electron at rest is what I consider it as A infinity. A free electron at rest is the electron which is far away from the nucleus, that is at an infinite distance from the nucleus, and it is assigned the energy value 0. So as the electron moves towards the nucleus, it is emitting energy and thus becomes negative. So the most negative energy value is associated with n is equal to 1. More and more amount of energy is released from when the electron is falling from infinity to n is equal to 1. And that is the most stable state for the electron of hydrogen. Right? I suppose I am clear till this. So what you need to remember is, more negative the energy of an electron, more close it is to the nucleus. This has to be very, very clear to you. How much ever the electron is close to the nucleus, the energy of the electron will be more negative. So you have to understand this very clearly. It is also possible to calculate the velocity of electron, magnitude of velocity of an electron. It is possible, but it is much beyond your level. So that is enough for understanding the Bohr's concept and the electron transition, how it is taking place, and what is the formula to find out that. All that you have done. Now, what are the limitations of Bohr's concept? It could not explain the spectrum of multi-electron atoms. He told only for hydrogen-like species, but he could not explain that of lithium or beryllium. As such, those atoms he could not explain. It could not explain Zeeman effect and Stark effect. Now, what is meant by Zeeman effect and